Welcome to topic 8.4, electric fields of charge distributions, daily video number 1. In this video, we will introduce the integral definition of the electric field and use calculus to derive the electric field for a point collinear with a line of charge. I'm Easton Landry, and I work at the Kinder High School for the Performing and Visual Arts here in Houston, Texas. So let's break down this equation, which is the integral definition of electric field. We have E. And here's the thing I want to point out. This is the electric field, both magnitude and direction. We don't see those little absolute value signs on either side. So this is everything all in one. We have that electric permittivity that's hanging out there. We have this dq, which is a differential charge element. It's not all the charge. It's a tiny little bit of charge. It can be both positive and negative because, once again, there's not the absolute value symbols around it. We have our r, which is the distance between the point charge and some point in space that's being squared. And lastly, we have this little r hat. It is a vector that's 1 unit long. We call this a unit vector, and we're going to review what that is here in just a minute, so it's okay if you don't quite remember. And it points from the charge element to the point in space that we care about. That's always how we define this by definition. From your charge, away from it is going to be your r hat. So there's no magnitude signs, and so plugging in the proper signs in this equation means you get exactly what you're looking for if you hold to it. Now that said, and I'll emphasize a couple times throughout this video, if you want to conceptually think through which way the direction is first, you can do that and not necessarily ignore the direction, but you can throughout the rest of the problem. Or, as we're going to demo in this particular video set, is we are going to follow the vectors exactly how they are to show that we get the proper conclusion. So let's review. What is a unit vector? Well, remember, if in the x direction we call that I hat, in the y direction we call that j hat, and then the z direction, which is going to be into/out of the page there, we're going to have our k hat direction. To find different vectors, we can have A, for example, which you can say is 3I hat, and that's going to be this vector. 3I hats adds up to A. On the flip side, I can have B, which might be a vector that's negative 2j hat. Well, j hat's normally up, so negative means down, and I need 2 of them, so that would be my vector B. This is what we mean when we have unit vectors to kind of help us find out direction. So in the end, we're going to solve for this number that's in front of either the I hat, j hat, or k hat, and that's going to be what we just say, hey, our vector is this many long in this direction. It's the I hat, j hat, and k hat that give us our directions. So let's warm up with a more straightforward example. In particular, a lonely point charge just kind of hanging out, doing its thing. Yes, we could solve this with Coulomb's law, but instead we're going to use the integral definition to show you how this all ties together. If we have our integral definition here, if I plug in the bounds, I'm going to be integrating from no charge to all the charge, negative q, which is there. And I'm going to plug in the distance that I am away, some distance d from that point P. Well, fun fact, that distance is a constant because this is a point charge. So I can factor that out, and I'm left with this integral. That's just the integral from 0 to negative q dq. Notice, though, I'm keeping my r hat, and it changed into an I hat. Why did that happen? Well, my r hat direction is away from the charge in the positive I hat direction. So if I keep that there, I have this little I hat that just kind of hangs out in my equation. Again, you can ignore that and just remember where it is conceptually, or we can follow it along as we're going to see happen here. Let's check this out. Once we have our I hat and we do our proper integral, we get dq, and we're going to have our negative q minus 0. Sure enough, we get a negative 1 over 4 pi epsilon naught q over d squared I hat. Wait, negative I hat, which direction is that? Yes, to the left, just like we would expect it to be. So if we're very formal with our unit vectors and our signs, it tells us the direction just from solving it. Or conceptually, you can say, hey, I know it's going to the left because it's a negative charge. Moving right along, if I'm sketching this one, we want to think of either endpoint and what's going to happen. I know that when I'm really close to the charge, I'm going to have a very, very, very negative value. And as I get further away, it's going to drift closer and closer to 0. It's not going to reach it. It's going to be asymptotic, but it's going to get closer and closer and closer. Well, if I connect these two in my sketch, sure enough, I'm going to get something that looks like that. So whenever you're sketching, think about your endpoints and what the curvature or whatever the values of what those endpoints have to be, and that can sometimes help you know exactly how to draw it. Let's look at a more complex example, the meat of this video as you were. We have a E field that's collinear. We're looking for the E field collinear with a line of charge. So here's our point. Certain distance x away from a rod of length L that has a total charge Q. The E field is going to be our integral definition, where it's going to be the dq over r squared r hat. Well, wait a second. dq is this little guy right there. It's a tiny little sliver of the entire setup. because all these little dq's, they're even smaller than that in reality, right, add up to equal the full thing. So if I look at that distance r away, that's where that r ends up coming from. This is what I'm trying to take the sum of all those little dq's, sum this one and this one and this one and this one and this one, all those dq's to find out what the total electric field is at this location. This little thickness is some thickness dr. Why does that matter? Well, because if we look at the density, which is a uniform density, Q over L, which is the charge of the whole thing divided by L, has to equal dq, this tiny charge element, divided by dr, the tiny little radius element. And we're summing up all those charges, or different way of thinking of it, summing up all the length till we get to the full length of that rod. So we manipulate this equation to solve for dq, and we're going to make that substitution into our equation up here to make it look like that. If we pull out all of our constants, like we did here to kind of clean up it, I hats, our constant, our q, and our l, we're left with this integral. Wait a second, where to get those bounds? Let's talk about that. So if we look at just the bounds, we have our distance x, and then we have our distance of x plus l, which is that full set there. That's where I'm integrating from. I'm integrating from this near side to the far side, and that's where those bounds came from. So let's keep this bottom equation in mind on this next page here. So we start with this one here. And the first thing we're going to do is we need to find out what is an integral of 1 over r squared. It's going to be equal to negative 1 over r plus c. Or if you were doing r to the negative 2, right, and you were integrating that, you'd get negative r to the negative 1. So if we take this integral and we sub our bounds back in, we're going to negative 1 over our final minus 1 over our initial. That double negative is something that students sometimes might miss, so look out for that. If we manipulate this all together, ta-da, this becomes a positive, moving it to the front. This is a negative, moving it to the opposite side. And sure enough, we get our final answer. This answer is perfectly fine and wonderful for the AP exam. But let's have a little bit of fun because I think it makes something really cool happen. Actually, sorry, I'm backing up one thing. We saw that this ended up kicking out a positive with our I hat. And sure enough, that's the direction this thing ended up pointing. Okay, we have this direction. Let's do something fun with this. So if we start with our equation that we had previously, we can make it so we have the common denominator. And when we do this, we're going to get to this relationship. If we sub that in, check this out. The L's end up canceling. It's kind of wild. And we get to this equation. Again, this is not required for the AP exam. You could have left it like this, and that's perfectly fine. But why did I do this? Let's see. If we look at edge conditions for this particular rod, and we make that L gets really, really, really tiny compared to X. So it might look something like that. What would happen to this equation? Well, if L is really, really tiny, we can basically say it goes away. And I'd be left with this equation. Where have we seen this before? Yes, it's just a point charge. Look, it even looks like a little bit of a point charge. So if you're really far away from a rod, it's going to just seem from a distance that it was a point charge at that location because of how it all works out and cancels. Super fun. Physics is awesome. If we graph this, we should then expect to have this thing look just like a point charge. If you wouldn't have expected that to happen, it's okay. We know it's going to decay at least a little bit. The beginning might be a little bit different, but on the AP exam, if we're looking for you to graph specific values, we're going to have you plot them. If we're looking for you to sketch, all you have to think about is, I know it's going to decay down to 0. I know at first it's going to be a lot. And sure enough, we get this 1 over r squared decay that ends up happening as we go through. So hooray, that was pretty cool. I just think that's fun to do for that setup. So what should we take away from this video? The main thing, this is the beginning of this process working with the integral version of the electric field. So what's the process that we followed? We drew our charge elements. We drew an effective picture with our r's and our r hats. We decided how we were going to integrate it in terms of that term. We wrote our density equation. We substituted known terms into the equation. We factored out constants, we wrote bounds, and then we integrated. But the things that I have here in bold are the things that you should focus on when you're writing this on the AP exam, because those are generally things that we give you 4 points, especially on a derive type problem. So writing the density equation, showing your substitutions, and writing your bounds. Integration, you're welcome to do it, and you should to get the final answer, but ultimately that might take you a lot of time. So my advice to you is move on in the exam and then come back if you have extra time to finalize that integration. One final thing to take away is to think of those edge conditions whenever you're plotting. Think of where you started, where you finished, connect those with your curves, and that's going to help you earn those points there as well. So with that, I look forward to seeing you in future videos exploring this equation some more. See you next time.